Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about internal resistances inside cells or batteries, for that matter. Here I have an example, and I also want to show you what a graph could look like after we plot the terminal resistance of a battery versus the current across it. So, before we begin, let me just fill this out here. The terminal voltage here's our equation, equals to epsilon minus I of the current and R for the internal resistor. So let's take a look at this circuit here to show you what each and every one of them represents. First of all, this this is the EMF of the battery itself. So that is the total voltage supplied by the battery, not including it being depleted by whatever little internal resistance is inside the battery itself. Here we have a diagram inside. We have this little R. This little R here is that little internal resistor of the battery itself. Okay, and then here we have the terminal voltage, which is in green. And this, if you imagine it, is basically the voltage that is supplied to the rest of the circuit. It's available for the rest of the circuit. Essentially, you take, what that is if you take this internal resistance or the potential drop across this little tiny resistor, you subtract that little tiny voltage drop from that of the battery. That's going to give you whatever is left over that is available for this rest of the circuit. Okay, so that's what terminal voltage is. If you also think about it, this terminal voltage is going to supply, or it's going to be the potential drop across this battery over here, which is the current in this loop, times R, which is this resistor on the external resistor that we have over here. So essentially, this is kind of, you can think of it as this is equal to the current on the going around the circuit times whatever resistance or resistors are outside of that cell. Here we have some dotted lines here. This dotted line here is to show the boundaries or kind of where your battery is. So imagine this is like your battery, okay? Okay, that's your battery. Actually, I probably have that on the wrong side. That's probably over here, okay? Oopsies. But essentially, here I have a question that I like to go over, and then maybe a relevant graph that might help you out for analyzing, say, a lab that you do for this unit. Example 1, calculate the following. If the EMF of the battery is 9 volts, so that's over here, that's the EMF. Okay, so EMF is going to be 9 volts, and the internal resistance is 0.220 ohms. We want to find the current through the battery if the terminal voltage is 8.8 volts, and B, if the current, if we know the external resistance, which is 5.5 ohms. Starting with A, which I'm going to do in this colored blue here. So we want to find the current. So we use the V terminal equation, which is just the epsilon, the EMF of the battery minus IR. To find the current, which is this guy over here, we just have to solve for it, which means we just have to rearrange this equation a little bit, which I will probably put this to the other side, subtract the terminal voltage across the EMF of the battery. So I'm going to get E minus VT. Okay, and that's equal to, this is moved to the other side, which is IR. That's basically saying the difference in the EMF of the battery minus what's supplied to the rest of the circuit, that little tiny bit of the potential that's left over should be the potential drop across this small resistor, this internal resistor. And if we know that drop, we know this tiny resistor, we know the resistance, then we can use that to find the current. So let's put in some of our values. This is 9 volts minus 8.8 volts which is going to be equal to 0.2 volts is IR, and our tiny little resistor is 0.220 ohms. So I is going to be equal to 0.2 volts, which is this side, divided by this R, okay, which is 0.220 ohms. This is going to give us, I get 0.909 or 0.90, and this is repeating. Or if we just round to two significant figures, this will just be 0.91 amps. Okay, there you go. That's the first question. On to question 2b. Okay, on to B. So for B, we want to find the current if this external resistor is 5.5 ohms. Keep in mind that if we're trying to find that, we can't assume that the terminal voltage is going to be the same anymore. We don't know that. We can't assume it's going to be 8.8. What we do know, let's write this equation out again. We do know things that stay the same are going to be this tiny resistor. That's going to stay the same. The internal resistance doesn't, it shouldn't change for this question. This EMF should not change as well. Everything else is free to change, and we can't assume that they will stay the same. So we've talked about this earlier. We said that the terminal voltage is supplied to the rest of the circuit, which is essentially the current times the external resistor, which is what we have, 5.5 ohms. So essentially, let's write that down. This is the external resistor times the current. So if I wanted to, I could substitute this guy in here, which gives me R is equal to epsilon minus I times small r, the smaller resistor, the internal resistance. And we want to solve for the current. Well, guess what? We'll just do some algebra and isolate for that I, since everything else should be the same as before. The resistance of that little resistor, the internal resistor, and the EMF of the battery, all of those three things will stay the same. Doing a bit of rearrangement, let's put the I's together. So I'm going to add this I on both sides of the equation, which that's small r. Okay, and this is going to give me IR plus I small r equals to epsilon, and we can factor out the I onto the outside, giving me I, and in brackets, big R plus small r is going to give me the EMF of the battery. And to solve for I, finally, let's just divide both sides by the sum of the resistances in this entire circuit, which gives me I is equal to EMF of the battery divided by the total resistance in the circuit, including the internal resistor itself. The volts of the battery, the EMF is 9 volts, okay, and the internal, the big R is 5.5 ohms. 5.5 ohms plus 0.22, which is the small one. So after we put everything in, we get 1.57, and that's rounded to how many sig figs do we want? We want 2 sig figs, so 1.6 amps. Okay, it's going to round to 1.6 amps. There you go. Okay, so that was question B. Notice that we can't assume certain things, and depending on what happens in your circuit, the terminal voltage and the current will change for that matter. Which comes to a point that I want to talk about is in a potential lab that you could be doing. You might be finding the relationship between terminal voltage and the current itself. So let's redraw this diagram here. So we have the battery, we have a little tiny internal resistor here, and let's say to change up this the current inside your circuit, you might have some sort of variable resistor that will be connected in series to the whole circuit. And in this setup, you might have, say, an ammeter connected in series to test the current, okay, which we will see what that is. And of course, we also want to find the terminal voltage. So keep in mind the terminal voltage could be here. You can find it by just attaching the voltmeter in parallel with this variable resistor, since it's going to be exactly the same thing ideally over there, assuming the wires have very low resistance. Okay, so even if you attach it over here, it's exactly the same thing. So it doesn't matter. I'm just going to write it down here because I have space down here for me to write this. So this is going to provide me with my terminal voltage, and that's something that we don't know. So after we change up this variable resistor, it's going to change our current, therefore changing our terminal voltage. This here will stay the same, the internal resistor and the EMF of the battery. Going back to that equation where V terminal voltage is equal to epsilon minus I small r, what we would generate is we would generate a bunch of by changing up this variable resistor, we then are going to produce a table of values for your current and as well as for the terminal voltage. Then guess what? We are going to graph this data. So if you graph this data, you're going to get something that looks like this. You don't believe me? Well, first of all, let me tell you what you're graphing. You're going to graph the terminal voltage against the current, just like how you would see this equation where if we compare this as y equals to mx plus b, y equals mx plus b. Well, you might notice that we have to rearrange this top equation a bit. To rearrange this to look like y equals mx plus b, you're going to get vt is equal to, well then, our x is actually the I, okay? The i's are x, because we're plotting that in our x-axis. So it's actually going to be negative. The negative stays, which actually explains why the slope is negative. It's going downwards, or downwards for your mirror image here for video taking. So the I and the R come together. I'm actually going to put the R first, the I second, to match the fact that the I is indeed your X. So that's going to tell you very much, because look, based off of y equals mx plus b, this small internal resistance is your slope. Haha, interesting, hey? If everything all works out. And last but not least, don't forget this epsilon here, and imagine there's an imaginary positive sign. So we're going to add epsilon, which means epsilon here is like our y-intercept. Okay, so this guy is our y-intercept. Okay, and this small r here, well actually the minus r is going to be our slope. Okay, so if we take a look at this slope here is technically going to be equal to negative r. So using the slope, you can find the internal resistance of the battery, and since epsilon is our y-intercept, that's this guy over here. This y-intercept, that should be the EMF of the battery. So, well, one thing we know for sure is you probably might be told the epsilon of the battery, which then will help you find a percentage difference. You wouldn't know what the internal resistance of the battery is, but you wouldn't be able to do a percent difference or percent error calculation for that. But anyhow, this is just one thing you could do with this setup is to produce this such graph to help you find the different components of the graph. So there we go. That is terminal voltage versus and as well as internal resistance. All right. Hopefully this video was helpful for you in solving this problem, and hopefully maybe your lab in the future. I thank you for watching. Good luck, and Fat Mama Physics signing out.